Okay, this video is the first in a series that aim at helping you how to do the more difficult computations in this course. So this video I want to talk about how to get the how to compute the steady state of the solow model. Before I do this, let me say a few words of advice about how to use these videos. So because these videos deal with technical aspects of the course, I think it's a good idea if you actually watch them several times. Also, don't hesitate to do some pauses with the videos and to put pen and paper to redo the computations as I present them, because the aim in the end is to allow you to be able to do these computations by yourself. Alright, so let's get on with the steady state of the solow model. So, as I said, the aim of the video is to be able to compute this steady state. So we'll take the very basic solow growth model in the case where you have a Cobb-Douglas production function. So before I actually show you how to compute this steady state, let me recall the definition. So the steady state is a state of the economy which is, let's say, permanent. So it's a state of the economy that reproduces itself from one period to the next one identically. So all the different state variables will be constant in the steady state. So what is exactly a state variable? Well, it depends on the model that we consider, but it's something that describes well the state of the economy. So especially in the solow model, the state variable that we'll have will be simply capital per worker. It will summarize everything that we know about the current state of the economy. So as I said, in the case of this video, I take a very simple Cobb-Douglas production function. So first, I'm just giving you the formula here of the Cobb-Douglas production function. So aggregate production, big Y, uses physical capital K and labor L. And so the production in period t, yt, is equal to at, kt alpha, lt, 1 minus alpha, where at is a productivity factor. So here I'm going to make a very simple assumption, two assumptions actually. The first assumption is that the population is constant, so lt is equal to L, and there isn't any kind of technological progress, so at is equal to a, so also a constant. So the first step here, before we actually talk about the steady state, is to rewrite the model in per capita terms. So we want to write small yt, which is GDP per capita, or income per individual. So small yt is big yt divided by lt. And you can see that very simply by getting rid of LT, we get that small yt is only a function of small kt alpha, function of kt, a kt power alpha, where small kt is the amount of capital which is available per worker. Now, if we want to find the steady state of this economy, there's a first step that we need to understand, which is how you get from one state of the economy to another one. And this goes through the law of motion of physical capital, which describes how capital evolves from one period to the next one. So we have this law of motion, delta kt, so the variation between capital in period t and capital in period t plus 1, so kt plus 1 minus kt, which is made up of two different things. So capital increases because first of the savings. So savings here, remind you, are a fraction of output, fraction s of output. where S is the savings rate and it's assumed to be fixed. So capital increases because of savings, SYT. And then capital is decreased, capital is destroyed because of what I've called in the course capital depreciation. So in each period you have a fraction delta, which is called the depreciation rate of the capital that gets destroyed because it is actually used up in the production process. So here we have the full law of motion. Delta kt is SYT minus delta kt. Now, because our state variable is small kt, capital per worker, we want to rewrite this law of motion in per capita terms. So here we have it. Delta small kt is S small yt, or S f of kt, minus delta kt. Now, in the steady state, this law of motion is very particular. The characteristic of the steady state is that capital per worker doesn't change from one period to the next one, so the variation is equal to 0. Okay, the steady state is such that kt is equal to kt plus 1 is equal to k star. K star is the notation for the steady state. So delta k star is equal to 0, which means in turn that the savings Sf of k star is equal to the depreciation delta k star. Or if you want to put it in words, you can say that at the steady state, investment is just enough to replace depreciated capital. So how do you write this equation in the Cobb-Douglas case? Well, replace f of k star by its expression. So you have SA k star power alpha is equal to delta k star. So at this stage, you have everything you need to find k star, which is the value of capital per worker at the steady state that we want to find. You see that in this equation, you have only exogenous parameters as A, alpha, and delta, and out of this we want to find k star as a function of these different parameters. So everything we need to do is isolate k star, put k star on one side of the equation and all the rest on the other side of the equation. So the best way to do this is here to divide by SA, because we want to get rid of SA on the left hand side of the equation, and also divide by k star because we want to get rid of the k star which is on the right hand side of the equation. This gives you the following formula. K star power alpha minus 1 is equal to delta divided by SA. And then at this point, you only want to have k star, so you need to elevate this equation to the power 1 over alpha minus 1. Here you are. K star is equal to delta over SA power 1 over alpha minus 1. Usually, we could stop there, but we just want to put this in a nicer form in order to be able to analyze this equation. So we'll just flip the fraction, and we'll get k star is equal to SA divided by delta. The reason I'm doing this is now the fraction is elevated to a power 1 over 1 minus alpha, which is positive, because alpha is between 0 and 1, so 1 minus alpha is positive. And then everything becomes much easier to analyze if we want to know how k star depends on S, A, or delta. So precisely here, as a kind of reflection on this formula, I'm asking you to find what happens when you change the exogenous parameters as A or delta, what happens to the steady state of this economy. So of course you can do this quite easily mathematically. know what happens, for instance, when S increases. But then you could also ask yourselves what happens in terms of economics. Okay, write some sentences, a couple of sentences to explain what is happening to the economy if we raise the savings rate. Alright, so this is the end of the video. To quickly summarize what you need to do in order to get to the steady state of the solow model, you have to first know how to write the law of motion of capital, then use the fact that at steady state capital is constant, and so the variation of capital is equal to 0, and so then you get a formula, an equation that allows you to fully compute the value of K star. Alright, that's it for now, so don't hesitate to review this video and feel free to ask questions either on the forums, Moodle forums, or when we see each other during the lectures.